Hello and welcome back. Hello and welcome back to Learning as a Hobby. Um, so I'm going to start on physics today. I read through section 1.1 and 1.2 in Classical Mechanics by John Taylor, and I took down some notes, and actually I did a few of the problems from section 1.2. I'll talk more about that in the video that I make about the problems. This video will be just on the notes that I took for section 1.1 and 1.2, and this video should be relatively short because section 1.1 and 1.2 are just sort of like an introduction to the subject. And in fact, section 1.2 is mostly about some vector algebra and calculus that you need to know. So this shouldn't be that long of a video. And because of that, you'll see when I get to the problem videos, the solutions to the exercises, I only did a few of them because most of the problems are vector calculus or vector geometry problems, which I'm sure we'll do either all of or most of in Schifrin's book at some point. So I didn't want to like repeat content. But anyway, let me get to the summary for section 1.1, 1.2 in Classical Mechanics by Taylor. Let me bring up my notes. All right, so here's the notes I took. He in the chapter, he suggests doing question number 1.7 and 1.15 in the exercise set for section 1.2, and I did both of those. So when I get to the problem video, you'll see I did both of those, and I did a couple other ones just for the sake of doing a few more fun problems. So we'll see those in the next video. Let's get into section 1.1. Section 1.1 basically just defines mechanics and talks a little bit about it. So the definition he gives for mechanics is the study of how things move. Some background about mechanics. It began with Galileo and Newton. In this book, we'll be focusing mainly on the three equivalent formulations of modern classical mechanics, which the three equivalent formulations were the ones by Newton, Lagrange, and Hamilton. So we'll start with Newton's formulation. We'll do Lagrange later on, and then Hamilton is like way later on in the book. But those are the three that we'll be looking at in Taylor's book, and these three formulations of mechanics are considered to be, what we mean by classical mechanics, right? So no relativity, although there is a chapter in this book on I think special relativity. I don't think he does general relativity in this because you need a lot more math for that. Okay, so that's basically section 1.1. Like I said, a very short, just like introduction to what the subject is. Section 1.2 is on space and time. And so he says Newton's laws are formulated in terms of these four things here: space, time, mass, and force. We haven't in this section, he doesn't talk about Newton's laws yet, but I think we'll do that in like the next section or some point soon, but just not in section 1.2. And we'll in section 1.2, he says we'll focus on space and time, and then we'll do mass and force in another section. Right, so for space, a lot of this is going to be review for what we did already in Schifrin, but anyway, whatever. We'll go through it. It's important just to see his notation because in physics they use a little bit different notation than they do in mathematics. So point P in 3D space can be labeled with a position vector r. And there's different notations that they use for unit vectors in this book. And I assume that it's the same thing throughout physics. So for example, x hat, y hat, z hat are the same things as the unit vectors I, j, k, which you're probably familiar with from vector calculus or from linear algebra, E1, E2, E3. They all mean the same vectors. I believe the E comes from the German word eins for one, and that's because these are unit vectors. They have length one. And then using that, you can write any vector, any point in space in terms of those vectors. So you get the coordinates as the weights in the linear combination of those unit vectors. Let me bring my pen up here. So for example, these are the coordinates with respect to the standard basis in R3, all right, for the vector R, right? And you can write it, using any of the notations. Right, and you can even write it as a three tuple, so R1, R2, R3, as long as it's understood which base, which I guess which basis you're using. I haven't talked about bases yet at all in any of the things that I've done so far, but the coordinate vectors that you're using, this thing here, this three tuple depends on the coordinate system. But as long as the choice of coordinate system is unambiguous, then it's fine to use this notation. As long, just everyone has to understand what coordinates we're using. All right. You can also use the summation notation, which is sometimes more convenient to write out the vector in terms of the coordinates. Okay, then he talks about some vector operations, things that we're already familiar with. You can add vectors together. You can multiply a vector by a scalar. These are the definitions in terms of the coordinates. You could take the dot product. You can find the magnitude. All of this stuff is things that we've talked about in Shiffrin in his section 1.1, 1.2. Same definitions, except we did talk about this formula in Shiffrin too. Yeah. So all the stuff we talked about already in Shiffrin. We haven't talked about cross product in Shiffrin yet, but this is the definition. I don't like using this notation for cross product for the determinant, because this actually isn't a determinant, but the formula is similar to a determinant, but he writes it this way in the book, so I'll just stick with that and not be a stickler. So the cross product is defined this way. So it's this strange, you get these the coordinates from the cross product. It gives you a vector, first of all, and it's this complicated formula for finding the coordinates of this new vector. And then here, just a note about some geometry. R cross S is perpendicular to both R and S with direction determined by the right-hand rule. The right-hand rule says if you take your index finger and your middle finger and lie them along the direction that you're taking the cross product, then your thumb points in the direction of the cross product. So either this way or this way. That's what the right hand rule says. And with magnitude RS sine theta. Here in this book, you'll see I'm kind of inconsistent in the way that I'm writing this, but where's my pen? He tends to write the magnitudes over here, just as the unbold-faced letters associated to the vector. So, in other words, for the vector R, I usually write an arrow on top, and same thing for S here on here. Notice I have arrows on top. But if you just write the letters here, by that he means the magnitude of the vector, the length of the vector. In Shiffrin and usually in multivariable calculus, we write the magnitudes like this, but in this book he writes it like that. Which it could be confusing, but if you pay attention, it's all right. But you'll see sometimes I'll lapse into, I'll use his notation, but sometimes I'll lapse just because I'm used to it. I'll lapse back into this notation. I try as hard as I can to be consistent with the notation used in the book, so it's not confusing. But because there's so many different notations for things, it's kind of like unavoidable that some of the things are going to be confusing. But it should be clear from the context, especially if you're paying attention. He gives some examples of, where some of these vector operations come along in, where you might see them in physics. So for example, the resultant vector, if you have two forces acting on an object, the resultant force is just the sum of the two force vectors. the resultant force here in Newton's law, F equals ma, is given by a scalar product. The mass is a scalar, and the acceleration is a vector, and so is the force. So here, this is an example of scalar multiplication. Work is a dot product. You take the product of the force with the dr, which is the distance, a small distance that you're traveling. Sorry, that the force is moving the object along. So that's an example of dot product in physics. That's called work. And the cross product shows up when you're calculating torque, which is denoted by gamma here. So if you have a force acting on a point that will rotate some point around the origin or something, then you can calculate the torque by taking this cross product. All right. Oh, I should say also, he gives some of these operations for vector, operations you can do on vectors here. There are a bunch of formulas in the exercises that, again, that I'm going to be skipping just because they're probably going to show up in Shiffrin, and I don't want to, do them multiple times. So, but he does ask you to prove a bunch of formulas that don't show up in the actual chapter itself in section 1.2. So you definitely at least want to look at all of the problems so that you're not missing any important formulas if if you're just using this book. So what else? Differentiation of vectors he defines. Again, this is something that we're going to do in Shiffrin, so I'm not going to spend too much time on this. But if you want to differentiate a vector with respect to time, it's defined to be the limit as delta t goes to 0 of delta r over delta t. Delta r is this difference of vectors on top. So, r evaluated at t plus delta t minus r of t divided by delta t, which is the small time interval. And it turns out that that's equivalent to just differentiating each of the coordinate parts of the vector r with respect to time. Right. And he does make a note here. The reason that this works, let me get my pen out again. The reason that this is equal to such a simple looking formula is because these vectors here are they're the rectangular coordinates. So these are constant with respect to time. There are other coordinate systems where that's not true. And if that's the case, then the derivative is a lot more complicated. So he just, mentions that in the text. And I'm sure we'll derive the formulas for those later on in the chapter. But as long as you're working with rectangular coordinates, this is a nice formula that you can use for finding the derivative. There's the sum rule for derivatives. There's a form of product rule for scalar multiplication. And again, there's more formulas in the exercises. So you definitely should take a look at those at least, if not, actually prove them yourself. The velocity is defined to be the time derivative of position. Acceleration is the second time derivative with respect to position, or it's the time derivative of velocity. Okay, the next thing he talks about is time. We're almost done here, believe it or not. Like I said, this is a very short, these are kind of short because it's a lot of review stuff. So in classical mechanics, we will assume time is a single universal parameter on which all observers agree, which in general is not true. For example, in relativity, we see that it's not. But for classical mechanics, that's, I guess, a characteristic of classical mechanics is that we assume that all observers use the same parameter for time. Okay, another important concept is the last thing he talks about in section 1.2, are reference frames. Almost every problem in classical mechanics involves explicit or implicit choice of reference frame, and choice this is the definition. A reference frame is a choice of spatial origin and axes to measure position, and a choice of temporal origin to measure time. And then he says here that choosing the right reference frame can simplify your work. Actually, in some of the problems that we will do in the exercises, you'll even see that because there's some problems involving dot product and cross product where you choose a convenient coordinate system to make the proof a little bit easier. Right, two frames in relative motion, which means one origin moving with respect to the other. That's what it means for them to be in relative motion. If you have such things, not all such frames are physically equivalent. So if you have two reference frames that are moving with respect to each other, they may not be physically equivalent, which brings up inertial frames. An inertial frame is a frame in which the basic laws in their standard simple form hold. So meaning Newton's laws. That's what he's talking about when he says the basic laws. Right, there's three laws that Newton like I said, we haven't talked about them yet, but there's Newton's three laws. That's what he means by the basic laws in their standard simple form. If the frame is accelerating or rotating relative to an inertial frame, the second frame is non-inertial, which means that Newton's laws do not hold in their standard form. Okay. This is the last thing I'll talk about here, and then I'll get to the exercises in the next video. Inertial versus non-inertial is central to classical mechanics and even more important in the theory of relativity. So this is going to be an important concept, I suppose, as we go on through the book. All right, so that's basically what he talks about in section 1.1, 1.2. The first exercise set starts on 1.2. So the next video that I'm going to do, which actually I'm going to do right after I finish recording this video, those exercises start for section 1.2. So I'll finish up a few of those, and then the next video I think I'm going to do is I gotta get started on linear algebra. So I'm going to do the first part of the linear algebra book that I'm going to do, and then I have to come back around for Schifrin and Spivak again. So let's take things one at a time. All right, let me just stop the screen share for a second. Okay, so that's section 1.1, 1.2. That's the summary. You should read the section itself again, because again, my summary is just a skeleton of the section. There's a lot of more detail that's in the chapter itself that you'll miss if you don't read the actual book. So do take advantage of that and read through the section before you try the problems on your own. I guess the last thing I'll say in this video is thank you guys for watching. When I started doing this project, I really thought that I was going to be speaking to myself, but it seems like some people have been watching, and it makes me really happy. I hope people are getting something out of the videos. I of course am having fun doing it myself too, and I hope that you're having fun maybe working through these yourself. So, or at least just watching. And learning something too. So that brings up the annoying part, which is if you do like watching this content and you want to see more, please do like and subscribe so that YouTube knows to share this video with other people that enjoy this type of content, and it'll help the channel grow. All right, guys, thank you so much. I'll see you in the exercise video for this section.